All right, so I wanted to really quick mention something that I didn't input into the original sets of things about the first section before I begin making section 2 notes about the AcDec math, and that is specifically this lovely thing that they mention called the binomial, oh my goodness, binomial probability theorem. So the binomial probability theorem, what is it? Why does it exist? So what winds up happening is in some cases we get things that are not the same percentage. And by the way, this does work in 50-50 shots. If we actually use the binomial probability theorem, we can utilize binomial probability theorem for things like coin flips and rolling dice and things of that nature. But the binomial probability theorem also plays a role in situations where maybe outcomes are not necessarily going to be the exact same. And that's what the ones that I want to focus on. For instance, on the test that you all took, one of the questions that was asked is about a girl shooting free throws. And I've got to find where that question is. It's number 18. And the question says, Zoe is shooting free throws at the end of the basketball game and her team is down by 1. She makes her free throws 70% of the time, and her free throws is independent from the last because she has nerves of steel. Obviously, we don't want it to be like, oh yeah, I made this one, so I'm going to be able to make the next one, and it'll have a higher probability. Although that can happen, but again, one of the interesting things about the binomial probability theorem is that we have to have the consistent success rate. How likely is it that Zoe wins the game for her team? So what do we know? She's down by 1. They're down by 1. She's shooting 3 free throws. And she has a 70% chance of success. We want to know the probability that she wins the game for her team. So in this particular problem, what we have to realize is that if she makes these free throws, she's got a lot of different ways that she could do this. Now, what we can do initially is we can actually, the most organized way to attack this problem would be create what's called a probability tree. And a probability tree looks something like this. On the first free throw, she can either make it or miss it. From now, I'm going to make this a check, and this is going to be an X. She has a 70% chance of making it here. Means she has a 30% chance of making it here, which creates a new situation. And so we've got some more cases. And on the second free throw, she has a chance to make or miss. Or she could make this one or miss this one. And again, this is a 70-30. This is a 70-30. So that's the second round. Then from there, each one of those, in her third shot, she has a chance to, again, just like in the last one, she can make or miss, make or miss, make or miss, make or miss. And again, 70-30. This is 30%, this is 70, this is 30, this is 70, this is 30. And what we can do is we can go through and we can calculate each one of these little branches. And the branches are actually fairly easy. Each one of these is a completely independent branch where we can go ahead and we can multiply along that particular stretch. For instance, if we came up here, this would be 70 times 70 times 70%, so 0.7 to the third. And that has a 34% chance of happening. Here, this is 70 times 70 times 3, so this is 0.7 to the second. times 0.3 is, ooh, this only has a 14.7%. Sorry, this is 34.3. We want all of that. This is 0.7 times 0.3 times 0.7. This is the same exact setup as this, so this is a 14.7% chance. 0.7 times 0.3 twice, so 0.7 times 0.3 to the second is 0.063%. Sorry, 6.3%. There we go. I keep doing them as percents. 0.3 times 0.7 times 0.7. This is 14.7 again. 0.3, 0.7.3 is up 6.3%. This is going to be another 6.3%. And then 0.3 to the third is 2.7%. And what's interesting is we can add these all up, and if I add 34.3 plus 14.7 times, there's that 3 times, plus 6.3 3 times, 6.3 times 3, plus 2.7. If we add up all of these probabilities, of course, there's a 100% chance that one of these is going to happen. Well, no kidding, we just came up with them. Now what we want to know is what's the probability she wins the game, which for her to win the game, she needs to make 2 or 3 free throws. I should probably put makes, not misses. So she needs to make 2 to 3 free throws. So that would be the following situations. That could be, come on, there we go, do what I tell you to do. That could be this one. That could be any of the 14.7s. And that's it. In those situations, she has won the game for her team. And if we add up those 3 things, 34.3 plus 14.7 times 3, we get that she has a 78% chance of winning. Now, that kind of stinks because we look at that and we see all the answers as fractional probabilities. But we could figure out, whoops, did that in the wrong thing. This becomes a 78.4% chance of winning, so that's pretty good odds. And we would say, okay, now we got to figure out 4 out of 5, that's definitely on it. 98 out of 125. Oh, there you go, 78.4 or 0.784, and you get your answer choice B. Now, this took some time to build. And if we thought that that was really annoying to have to do it this way, you can imagine how this is going to be if we're doing a problem where we've got 10, 11, 12 attempts. In fact, I believe at one point in time, just looking through my problems, number 28 required binomial probabilities. That was 4, so you would have had to have done 4 layers on that particular question. I think there was another, I thought there was another binomial probability question. I'm not seeing my other binomial probability question. Nope, no other binomials that I can see on this particular battery of questions. But you can see that this is not exactly a enjoyable problem. So how do we get around that and be able to make this work? Well, so what I notice, first off, is let's deal with, so what is the binomial probability theorem? The binomial probability theorem states this. The probability of an event with, what is it P? Oh, how many times? N. With N attempts, P is going to be the probability of success. Q is the probability of failure, which is just 1 minus P. And R is the number of successes. Now what we can do is we can actually write an equation for that. The first thing we need to realize is if there's r successes, then what we do is we take the probability of a success and raise that to the rth power. That would be how many successes multiplied by each other. And for this, we would have q then to the n minus r. This can be seen right here. I wanted 2 successes. So when I wanted 2 successes, I needed to multiply 0.7 times 0.7 times 0.3, because in that situation, I needed to have that 0.7, that 0.7, and that 0.3 multiply out, and I could just say 0.7 squared times 0.3. If I had 3 successes, I would want 0.7 to the 3rd power, 0.7 times 0.7, 0.7, and the 0.3 would be to the 0 power. Again, we're taking 3 shots, so we could see that the p in this case, 0.7 would be a 3, the q would be that 3 minus 3, which would give us our 0. So r plus this number plus this number should equal this final value n. Now this is where things get weird though. You'll notice that there was only one way to make that 3.4, and there were 3 ways to make that 14.7 where I made 2 shots but missed 1. We can come up with that number by using some counting principles. I don't care the order in which I wind up sinking these buckets, I just care that I made 2 out of the 3. So how many ways can we do it? Well, there are 3 shots, and I wanted to make 2. So the first and the second could be a combination, the first and the third could be a combination, and then the second and the third could be a combination. And I've used the word now combination, which tells you, oh, combinations. That's n attempts taken r times. In this case, going back to my problem, what I could do is I could realize that there are 2 situations where I'm going to make the game win. I'm going to make 2 or 3. So what I do is I say, well, we have 3 attempts. I want to make 2 of them. 0.7 to the second, 0.3 to the 1, plus there's also the chance I could make 3 of them. There's only one way to do that. And that's 0.7 to the 3 times 0.3 to the 0. And if you do that, you get the same exact 78.4% I was talking about. Let's take a look at another situation. That was number 18. Let's take a look at another one where the binomial probability theorem came into play. Or that was number 18. Where else is binomial probability theorem coming in? There we go. Okay, so number 8, we have Carlos, who's writing his 35-question math test for his students. And each question will have 5 answer choices. What is the probability that the letter E will appear in the answer exactly 7 times in the exam? So again, we're randomly assigning. We want to figure out the probability of there being exactly 7. So this is binomial because either E is the answer or it is not. Binomial, and I didn't mention this earlier, but binomial just means it's a yes or no question. Binomial probability, so the answer is either E or it's not E. What's the probability that my answer is E? That's actually going to be 1 out of 5, or 0.2, depending on who you are. Now, you're probably going to want to leave it as 0.5 because the answers are really gross fractions, but honestly, if you have to check by just typing in the numbers, cool, whatever. So that's going to be your probability of E. So the probability of not E, I know, it sounds weird, is going to be 4 out of 5, which is 0.8. So what I can do with this problem, because it's binomial, is I want exactly 7. So how many ways could there be 7 E's in the problem? Well, there are 35 questions taken 7 combinations. I don't care about the order of which they get picked as E's. I just care that there are 7 problems with E that exist. So there's that. Out of that, I've got 1/5 to the 7 times, and I'm going to multiply that by 4/5 to the 35 minus 7 times, which last time, hopefully I can do math, is 28. And if I type that into my calculator, I can get an answer. You probably can't math enter that particular question. It's gross, it's terrible, it's horrible. You don't want to have to deal with it. You do wind up with 5 to the 35th power in the denominator, but that doesn't help you either. Just the 35th is 2.9 times 10 to the 24. Yeah, that doesn't help you at all. You get a whole bunch of numbers. It does cancel out and reduce. What I would suggest is realizing once you get your answer, clearly it's not 1/2, 1/5, or 7/34, so you could easily check. I would then check the E answer, and if that doesn't come up with my right answer, I will answer the I'll answer the big, huge, nasty looking thing. So that's binomial probability theorem. I hope that that was useful. I hope you found that at least easy, because it's not a terribly difficult one. The biggest thing is when do I use it? And the answer is anytime I'm doing something that is independent of each other. So drawing cards is not a good choice, because as soon as I take a card off the top of the deck, the deck has gotten smaller, so the probabilities have changed. So anytime that, like flipping a coin, that would be a situation where probability is independent. Taking a die and rolling a single die over and over and over again is going to be an independent situation. Replacement will be an independent situation, so that pulling things out of a bag with replacement is independent. So any of those things will allow you to do binomial probability. Hope that was helpful and useful. And after this, I will begin the geometry stuff, so it'll be fun. Thank you very much. Bye.